To today's colloquium. It's my great pleasure to introduce our speaker, Professor McCluskey, who, of course, doesn't need a large introduction since he's very well known in the department since many, many years. So Matt got his PhD from Berkeley, working under Eugene Holler, working at Lawrence Berkeley National Lab in 1997. Then he went on to do a postdoc at Park Xerox, where he worked on semiconductors used in blue lasers. And you remember, not too long ago, blue lasers actually got Nobel Prize. And in 1998, he joined WSU. He's got a very broad research background in high pressure and materials physics. His group also develops optical techniques such as confocal microscopes, and which resulted in a startup company, Clark Scientific. There. He has co-authored or authored over 100 peer-reviewed publications and 2 textbooks. He's very well known in his field of research. For example, his article on defects in zinc oxide has received over 1,300 citations. He has received a number of awards. For example, he's a senior member of the National Academy of Inventors that happened in 2022. And here at WSU, he's the Westinghouse Distinguished Professor in Material Science and Engineering since 2013. And very recently, he also was elected an APS fellow. So we are very happy to have him here and have him talk to us on physics of crystal colors. Please welcome.
Thank you, everyone. And today I'll be talking about some research we've done and others that have been done by other people. And the research we've done has been supported by Air Force, Department of Energy, and National Science Foundation. Okay. So, all right. So, as Peter mentioned, some of my research interests are defects in semiconductors. This was a meeting that was held in Seattle that I chaired. This is a textbook that I wrote with my late advisor, Eugene Haller. We look at semiconductors under pressure. This is work done by Lauren Barmore, who is now at Livermore. And we have a startup company which does photoluminescence and Raman imaging. And just in general, optics and spectroscopy is an interest of mine, and that's what I'll be talking about today. So my current graduate students are doing some very interesting projects. I'll talk a little bit more about that work. Is looking at persistent optical effects in potassium tantalate. Julie Miller is looking at semiconductors under extreme pressures and also variable temperature. And Apolypsa is looking at photochromism in a nonlinear crystal, barium gallium selenide. And so the outline for this talk, I'll be focusing on semiconductors or insulators, looking at some basic optical properties, optical absorption and emission, doping and how that affects the appearance of a crystal, and so-called hydrogenic impurities. And so the basics, when you look at of course, the electronic properties of semiconductors are very important, transformational, and the optical properties are also extremely important. So the first thing you can ask is about optical absorption of something. Can I see through it? And so a semiconductor has a band of energy states, the valence band, and in a pure semiconductor, they're completely filled with electrons. And then we have this band gap where there are no states in a pure crystal. And then there's a whole another range of states, which is called the conduction band. And so an electron can be promoted by a photon comes in, can be promoted from the valence band into the conduction band. And when that happens, that photon is destroyed. And so you can see that as absorption versus photon energy. You'll suddenly get a large absorption above the band gap energy. But below the band gap energy for a pure semiconductor, it's transparent. So if you see a crystal, it's transparent, you at least know that its band gap must be, greater than 3 or 4 EV. So silicon has a band gap of 1 electron volt, and so you can't see through it. That's in the infrared. Gallium phosphide has 2.2, which is in the reddish orangish part of the spectrum, and so it has that reddish orange color, but blue and green are absorbed, and so that's why gallium phosphide has that orange color. And then gallium nitride, it has a band gap in the ultraviolet, so it's transparent. Whatever color you see is due to defects. Along with absorption, you also have the possibility of emission. So light can emit, and suppose you manage, okay, to get an electron into the conduction band and a missing electron or a hole in the valence band. The electron will definitely want to get back to the hole. It's called electron-hole recombination. And when it does so, if it does that by the emission of a photon to conserve energy, then you get a peak in the emission spectrum. So this is plotting how many photons you get out versus photon energy. And it's pretty close to the band gap. So that's another way to estimate this band gap property. And it's the basis for light-emitting diodes. You electrically inject an electron into the conduction band and a hole in the valence band. And this process results in whatever color light you want, which depends on the band gap. So you can tune the color. So really, to make semiconductors useful, you need to dope them. And so we have 2 types, N-type and P-type. So if you put in a deliberate contaminant or a dopant, which is a donor impurity, it has 1 extra electron. For example, phosphorus and silicon. So phosphorus has 5 valence electrons. It replaces a silicon that has 4. So that extra electron is available to go into the conduction band. So a little bit of thermal energy is enough to put the electron into the conduction band. So you put lots of donor impurities in your material. N-type, meaning negative conduction. The other thing you can do is put in an acceptor that is deficient 1 electron. And in that case, it can accept an electron from the valence band, leaving behind a positively charged hole. And those holes are just like particles. They can carry current. They're positively charged. They have mass and everything else. So that's called p-type because those charge carriers are positive. Now, so it helps to, if you want to make a device that operates at room temperature, you want this energy to be pretty small so that, the thermal energy is enough to promote the electron. And so that gets us to shallow or so-called hydrogenic donors and acceptors. This is an example of phosphorus and silicon. So phosphorus has that extra electron. The electron leaves the phosphorus, but it orbits around in a hydrogen-like orbit. So it's just like the Bohr atom. You have a positively charged phosphorus, and the negatively charged electron goes around. You have an effective dielectric constant that screens the electric field. So instead of 13.6 eV binding energy, you get something like 20 millielectron volts. So it's much smaller binding energy. So low binding energy. And what goes along with that is a large Bohr radius. Other than that, it's essentially like the hydrogen atom. And then you can also have acceptors doing the same thing. So you have a negatively charged boron, which has acquired an electron from the valence band. And that hole then orbits around the boron. And so it acts like, anti-hydrogen, if you will. Okay. So just like the hydrogen atom, these impurities have 1s to 2p transitions that you can see with optical spectroscopy. And so this is a beautiful spectrum at low temperature where you see the 2p0 and 2p plus minus, 3p0, 3p plus minus. What the plus and minus is that there is some splitting because this thing is in a solid and not in vacuum. So those do have some splitting, and it's related to the different band curvatures in this direction or that direction for the conduction band. But other than that splitting, it's essentially, it's a 1s to 2p transition, and you see those as sharp peaks, 1s to 3p, 4p, and so on, and a little continuum absorption. So this is in the infrared. So these energies are in the tens of millielectron volts, far infrared. So if you had infrared eyes, you'd say, oh, that seems to have been doped. It looks different, but it doesn't look any different to the human eye. But there is something that you can see, and that is boron in diamond. And it acts a lot like boron in silicon. Okay, it's an acceptor. It has these 1s to 2p like peaks, has continuum absorption, and a couple other peaks that are interesting. But the point is that the threshold is 300 millielectron volts, so it's a deeper acceptor, higher energy to ionize it. It's still not in the visible, so this is all in the infrared. But if you keep looking at this absorption profile into the visible, it actually does absorb strongly, reasonably strongly in the red, and a little bit in the green, and not at all in the blue. And so that results in these wonderful blue diamonds, which are called sometimes called type 2 diamonds. The most famous of which is the Hope diamond. So this is a picture, and I have to say, I've seen it, and it doesn't look this big or this blue. But it's still really impressive. So if you're ever at the Smithsonian, check it out. It has an interesting history. It was first known in 1668. It was sold to one of the King Louis. It was 112 carat at that point. And it was recut by a court jeweler into a beautiful diamond that was 67 carats. You know, a pretty large diamond by jewelry standards is, I would say, 1 carat. I mean, that's pretty decent size. Then it was for some reason stolen in 1892 when things fell apart. So it went missing, but it resurfaced in London as a 40. It had lost some weight. It was 45 carats. And it was purchased by Henry Philip Hope, and that's who it's named after. And then it found its way to the United States. Joseph Frankel's and Sons owned it around the turn of the century. It was sold to a very rich woman, Evelyn McLean, who wore it for many years proudly to various social events. And finally, almost finally, it ended up with Harry Winston Inc., a company in New York, who then donated it to the Smithsonian Institute, where it is today. So that's the most famous boron-doped semiconductor in the world. And when I say semiconductor, we're very generous. So a semiconductor is essentially anything that's not a metal, almost. People used to call them insulators, but now that we're doping them and making devices, insulators have now become semiconductors. So those I talked about, those are hydrogen-like impurities. There are also lots of things that are called deep levels. They have energy levels that are far away from the conduction band or the valence band. And they go by various names, F centers, etc., titanium, iron, chromium, and then more recent work on gallium oxide I'll touch on. So the key part of this is the question of localization of the electron's wave function, or the hole's wave function. So for a shallow acceptor, as I mentioned, has a large Bohr radius, and it covers many, many unit cells. And so you can treat the crystal as a continuum. So it's a delocalized wave function. But a deep level is different. This is an example of maybe I have lithium and zinc oxide, and the whole wave functions are located on neighboring oxygen atoms only. And so that's more of a chemist thing. It's more like a molecule rather than this continuum. And so the localized wave function, much smaller wave functions. And that has a few implications. So since we're talking about how crystals look, we have what's called a coordinate diagram, which it just means the position of the defect, essentially. And you can excite, let's say we have a negatively charged defect. If you move that defect this way or that way, it's like a harmonic oscillator potential. So it has its equilibrium position. Then if you excite an electron to an excited state, now the thing is in a neutral state because you pop the electron off. But you can excite it into various vibrational sublevels, n equals 0, 1, 2, 3, 4. And so these are all possible transitions. And so what the short story is it tends to broaden the absorption peak. Instead of having a sharp line, now we have this big, broad, vibrationally broadened peak because of all these vibrational modes that it can go into. So you have a whole range of energies. These are actually useful. So the early days of defects were centered around things called F centers. F is standing for Farbe, which is German for color. So they're color centers in alkali halides. And so we have potassium chloride shown here. It's found in sea salt, I guess, but there are lots of them. So we have lithium fluoride all the way potassium iodide. And these are classic salt crystals, plus minus, so crystal structures. And so if you irradiate this, let's say with electrons, you can damage the crystal. So you can knock out a chlorine atom, creating a vacancy. And you create lots of electron hole pairs because the X-ray has lots of energy. So the color center is a vacancy, like a chlorine vacancy, with one electron inside. And that acts a little bit like an electron in a well. And you can, as you know, you can excite an electron from the ground state to an excited state. And so that's what we're seeing here. The electronic excitation from the ground state to some excited state gives us a peak. And lithium fluoride has the smallest lattice constant, so it's the most confined well. And so it has the highest energy. And that's like 252 nanometers, which is way in the UV, the deep UV. And then you can go all the way down to 688, which is like deep red for the large crystal. And here's a couple of pictures of KCl and KBr. And they have a magenta or cyan type of color, depending on where that absorption peak is. Okay. So this is actually useful. It's used as dosimeters in radiation to detect whether you've received, too much radiation. Thermoluminescence is one of those properties that's used you have your badge, you've been working at Chernobyl or whatever, and then you come back and they put it in the machine and they say, okay, let's see how much damage there is in this crystal. And so thermoluminescence is an interesting technique. So so we have this anion vacancy, like a chlorine vacancy with an electron, and it's stuck at room temperature. But you can raise the temperature to release that electron. And it might go up, it might go down. But when it goes from this level of an impurity to this level, different impurity, it actually emits light. So that process, so you excite the electron up here and somewhere it gets captured and then falls down, and to conserve energy, a photon is emitted. So you ramp the temperature up and see how much light is produced as you get hotter and hotter. And so you get these various glow peaks, and you can the glow curve is what it's called. And you can detect the emitted light and say, all right, based on this profile, we've calibrated it. We say, you've received this much radiation. Okay, so still to this day, they use these techniques. Another jewelry crystal is the blue sapphire. Some people, the gem people call, if it's not blue, they usually call it something different, but it's always sapphire. And what makes sapphire blue are two things: the combination of titanium impurity and iron impurity. So just naturally in the earth, those get mixed in with the sapphire. Sapphire is aluminum oxide. All right. So why does it have this blue color? Turns out there's an interesting thing that happens. There's a titanium that's next to the iron. And you can excite an electron from the titanium to the iron. Essentially, it's an excited state where the wave function goes from here to there. Okay, and that's called a charge transfer. And there it is. And so it results in a broad emission. This is showing from 400 to 900 nanometers of wavelength. People can see from 400 to 700. And this broad absorption is attributed to these pairs. And because that absorption is around 600 nanometers in the reddish orange and not much absorption in the blue is what you see. And then a really common impurity in all kinds of oxides is chromium, and specifically the 3+ oxidation of chromium. And here's an example of chromium in some crystal, and it's in an octahedral environment. So it's surrounded by 6 oxygen atoms, and the dashed lines show this 8-sided shape. It's called an octahedron. And chromium can be in various crystals. If it's in aluminum oxide, we call it ruby. And the absorption shown here is in the green curve. It absorbs in the violet and the green yellow. It has strong red transmission, and so it gives it this red color. So these absorption bands are due to exciting an electron from its ground state in the chromium to an excited state. So the d electron going to a higher energy level. Now, if it's in a crystal called beryl, which is beryllium oxide with some other elements, then that's called emerald. And the absorption bands are slightly different, but it's the same basic physics. It's just that they're different enough so that there's strong blue-green transmission, and we see emerald as that wonderful green color. Now, the ruby is the basis for the first visible laser. And so this transition, this is emission I'm talking about now. So it absorbs a photon and decays to this level called E2. And that transition from E2 to the ground state is what gives you the red photon. Okay, so that was the first visible laser. Now, in gallium oxide is an emerging material for high power applications. Very exciting material. Chromium is always an unintentional impurity, but to study it, we, with the group of John McCloy, looked at deliberately doped chromium-doped gallium oxide. So there's the chromium, and it's a little more like emerald. It has a greenish color. These are the absorption bands due to the electronic transition. This is the bandgap of gallium oxide, which is around 4.5 electron volts. So that's the fundamental absorption. And these absorptions are due to the impurity. And that gives it the greenish color. And early on, we discovered that crystals contain iridium. And I didn't even know how these were grown. And so I went to the late great Kelvin Lynn, and I said, I think we see iridium in these crystals. It seems so weird. I mean, there's dinosaur extinction, but that's not relevant. Well, okay, it turns out that these crystals are grown in iridium crucibles. So that was the reason. Iridium is a very inert metal, and so at high temperatures, it tends to not oxidize. And, it's basically the go-to material for these oxide crystals. So what you do is you have a melt inside of an iridium crucible, and you pull up on the melt and you get the crystal. Well, in the process, there are iridium impurities in your material. So we discovered that it's a deep donor, so it can donate an electron. And if we dope the crystal with magnesium, which is an acceptor, then the electron will be compensated by the iridium. So, the magnesium will be compensated by the iridium. And what that does is it just donates its electron to this acceptor. So that results in the so-called iridium 4+ oxidation state. And then magnesium is negatively charged. So interestingly, iridium itself, you can have a couple of electronic transitions. First is the valence band to iridium transition, and that is just an electron from the valence band going to the iridium level. And that results in this absorption threshold around 2.7 eV. You can also have what we think is an internal transition, just a D level to another D level that gives this other bump in the absorption. So what you see is that it absorbs, so you get a loss of transmission in the visible. So 2.7 is just getting to be about blue-green. And so it results in a yellowish color. By the way, zinc dopes showed qualitatively the same spectrum. Zinc is another acceptor. So we knew that this absorption was not due to the magnesium because of that. So it has this kind of interesting yellow color. If it doesn't have the yellowish color, the crystal grower immediately knows that something went wrong. So my student, Cassie Rempel, who is now at Sandia National Lab, looked at electron irradiated gallium oxide. That's another way to damage a crystal. Shoot electrons at it. The as-grown material was heavily N-type, so highly conducting. And here's the as-grown crystal. Mostly transparent, but it has a little bit of a grayish tinge to it. When we bombarded it with 0.5 MeV, it was done in France. I didn't do it myself. Nothing much changed, but with 2.5 MeV, it changed into this yellowish color. And this is showing the transmission versus wavelength, and it's just verifying. So these two curves correspond to these two pictures, you know, and pretty flat. But the last curve has this dip in transmission around 400 nanometers. So it's really like a kind of an old, like if you have an old white shirt that turns yellowish, it's because not enough of the blue is in there. And so this is the same thing. It's cutting out the blue, and so it gives it a yellowish color. The eye is a terrible spectrometer. I mean, lots of things look yellow, and then you look at the spectra and they're quite different. But so where is this coming from? We think it's coming from a defect, a gallium vacancy, and an electron from that missing gallium point is being excited to the conduction band. And so there's a threshold in absorption. Notice the energy, which is proportional to 1 over the wavelength. Okay, so vacancies can result in color. Now, in the infrared, we have free carrier absorption. Free carrier absorption just means that if you have electrons in your conduction band, they can be excited. Another way to look at that is Drude absorption. So if you have an electron, you have an electric field going back and forth, that's going to accelerate the electron back and forth. And so that's a way the electron can absorb energy from the electromagnetic field. And it tends to get stronger with longer wavelengths. There are lots of, by the way, there are many units for wavelength. And so this is another one, wave numbers, which is just 1 divided by the wavelength. So you get to long wavelengths towards the left, you get strong, really strong free carrier absorption. And then as you go to the visible, there's still some absorption, and that gives it that kind of grayish color. And then, oh yeah, right. So then when you irradiate it with electrons, it becomes insulating, and so the free carrier absorption totally goes away. Okay, so the final part of this talk is, now that we have looked at a few examples of how crystals can become colored, we're going to now use light to change conductivity and color. So this is 2 connected phenomena: persistent photoconductivity and photochromism. And so what is photoconductivity? If I have a defect here, it has an electron sitting on it, let's say, and I come in with a photon, you can excite it. And so we already saw examples of that, how that results in a change in the appearance of the crystal. But it also means, hey, we've got now an electron in the conduction band, which can conduct electricity. You can measure that electrically. And so that's used for detectors, infrared detectors, all kinds of sensors. Now, photons can excite a carrier into the band, which increases its conductivity, so photoconductivity. Now, persistent photoconductivity, or PPC, is where the carriers remain even after you turn the light off. Okay. Sometimes for a few minutes, sometimes for much longer. So my student Macarena has been looking at potassium tantalate. It has a band gap of 3.6 eV, so that's well into the ultraviolet. Oxygen vacancies, missing oxygen atoms, act as shallow donors. And to give it this persistent photoconductivity property, first it's annealed in hydrogen at 800 degrees, and then exposed to light near the band gap, 340 nanometer light. And that results in persistent photoconductivity, as I'll show. So here's the evidence for persistent photoconductivity. Using Hall effect measurements in our lab, we measured the resistivity, Macarena measured, before exposure to light and after exposure to light. And so there is some variability depending on, from sample to sample. But you notice that before exposure and after exposure, there's a 1, 2, 3, 4 order of magnitude drop in the resistivity. This is at room temperature, and it lasts for many hours, in fact, many weeks. So there is some recovery as it drifts up like that, but it's pretty slow. You would have to wait. So it's a 4 order of magnitude increase in conductivity, and to fully recover, we extrapolate that you'd have to wait a couple of years for it to get back to its original resistivity at room temperature. So really persistent. This is also can be seen with IR absorption. As I mentioned, free carrier absorption allows you to see the electron concentration without having to attach wires. And this is the free carrier absorption shown at low wave number, long wavelengths, it's stronger. And if you look very closely, there is a peak that appears after exposure to light. What we're actually plotting here is the difference. So the difference in absorption before and after exposure to light, to the UV light. Let's see. So that is identified as an oxygen-hydrogen impurity. So it seems that hydrogen is involved in this extremely long-lived persistent photoconductivity. So that was a clue as to the mechanism. Well, here's our defect model. And the other clue was that it only works if you anneal or bake the sample in hydrogen. So hydrogen is key. So when it's annealed in hydrogen, hydrogen replaces an oxygen atom. What that means is that the hydrogen is occupying the oxygen site. So these red atoms are oxygens. Now, essentially, this is a proton and 2 electrons in a site that otherwise would be an oxygen atom. So we come in with a photon, and what happens? It causes the defect to explode. What I mean is everything leaves. So the 2 electrons leave, the proton leaves, and the electrons go into the conduction band. In essence, they're free to conduct electricity. So that's where you get the reduction in resistivity or increase in conductivity. And the hydrogen, the proton leaves too, and it binds to some oxygen atom in the crystal. We're not sure exactly where, but that bond is strong enough so that at room temperature, it's metastable and it will last. It'll stay there for a long time. So we think the hydrogen is the key ingredient to make this very, very persistent. Now, the connection with photochromism, I think, is very interesting. In fact, I believe that when you have photochromism caused by point defects, hydrogen is probably lurking there somewhere. So what is photochromism? Photochromism is, if you have those glasses when you go outside, it's a material that when you expose it to light, it changes color. So its transmission spectrum changes after you expose it to usually ultraviolet light. So that's just kind of shown here. You have these darkening glasses that are transition lenses, things like that. Smart windows, you know, that darken when it's getting hot outside. It's a very interesting topic. So going back to potassium tantalate, before light exposure, Macarena measured the transmission spectrum. Here's the bandgap absorption right here. The transmission drops right where it should. And it's pretty flat. This is just an artifact here. It's pretty flat over a wide range. But after light exposure, remember we get lots of conduction. This low transmission at long wavelengths is due to free carrier absorption. However, in addition, there's a dip right at 400 nanometers. And that is attributed to some defect, which I think is iron, but we're not sure. That is changing its charge state and then becoming optically active, and now has this peak. So it's a signature, if you will. And here's just a couple of pictures. It definitely has this kind of dark grayish color. And so this defect is very, very interesting. And it's definitely something that we are continuing to study. So the darkening is due to the combined effects of free carrier absorption, which goes into the visible somewhat, and then this mysterious defect peak. If it weren't for hydrogen, you might be able to get that defect peak at low temperature. But hydrogen really allows you to do these things at room temperature. Makes everything very, very persistent. Okay, so then the last example is copper doped gallium oxide. I mentioned gallium oxide already, and there's iridium from the crucible. Iridium actually has an infrared signature that we can see. And copper in the 3+ state has a visible absorption band. The 3+ state is very rare. You will not find it in nature, but it's here and there, it's been seen, and it has this broad absorption in the visible. So you can tell, use that to tell what oxide, the 2+ and 1+ do not have those. So again, iridium gives an electron to copper. So when you receive your crystal, the copper is in the 2+ state, iridium is in the 4+ state. And that's just shown in this picture here. It's not exactly transparent, but it's clearer. Before light exposure, there's sort of a flat absorption profile. These are offset for clarity. And this is showing in the infrared. And on the right is just a picture. So after light exposure, it turns dark, kind of a brownish color. And along with that, in the infrared, we see these distinct peaks that we attribute to oxygen, hydrogen, vibrational modes. So just to summarize, exposure to 275 nanometers, we think turns the copper 2+ into copper 3+, giving it this color. Persistent at room temperature, lasts a couple of weeks. And hydrogen peaks also appear. Hydrogen, once again. And so I'll show you these peaks. Again, has grown. We darken it once, we get these hydrogen modes. We anneal it at 400 degrees in air, that's just on a hot plate, and it erases everything. Then we try it again. And so we darken it again, and those peaks reappear. So the appearance of IR peaks says we're forming these OH bonds in the crystal. Now the iridium is telling us something else. So the iridium peak, this is due to the iridium 4+. When we darken, it actually decreases in intensity. So we think iridium 4+ captures an electron, turning it into 3+, which is invisible. You repeat the experiment, comes back when you anneal, and then darken again, and it decreases again. Okay. So what's going on? This is a little more complicated, but it's a similar story. So we start with this hydrogen substitutional. Again, that's a proton and 2 electrons on the oxygen site. But next to that is a copper atom. They would call it copper 2+. Now, when we expose it to light, that excites the electron. The electron gets captured by the iridium, and that causes the iridium peak to go down. All right. Well, now this new charge state is unstable, so the proton leaves and attaches onto an oxygen atom, and that forms the OH infrared modes that we see. So just to summarize, when we expose it to light, hydrogen is liberated from the vacancy, forms an OH bond, and that is, metastable at room temperature. But the electron, instead of producing PPC, conductivity, the electron gets trapped by the iridium. So we do not get conductivity thanks to the iridium. It would be interesting to try this on a different crystal that did not have iridium and see if it showed PPC. So that's, I told the program manager that's our story and we're sticking to it. It's a little bit convoluted, but I think that the overall theme is that with this stuff, is that if you have a point defect, if you have photochromism that's very, very persistent, you should look for hydrogen. That's my takeaway. People accuse me of being obsessed with hydrogen. I plead guilty. So just to summarize, there are a few ways that crystals can absorb light, and I haven't even talked about polarization and stuff like that. There are lots of interesting phenomena. Band to band, so pure crystals can show colors, but more often defects are the things that give crystals color. Hydrogenic impurities like the Hope diamond, F centers, which are native defects that are in alkali halides. Deep level impurities can give oxide crystals, these colors like ruby, sapphire, emerald. And photochromism, where you're actually inducing changes in the color of crystals by exposing them to light. And this is a really interesting field, I think, for 2 reasons. One is it's showing the connection between photoconductivity and photochromism. And 2, it might have some very interesting technological applications where you can change the color of a filter and in essence have a very, very cheap spectrometer. So that's about all I have to say. So thank you for your attention.
Thank you for this colorful talk.
Yes.
Questions? Let's start with Fred.
Yeah, this is really interesting about the persistent photoconductivity. You're basically making it into a different, can you make it into a different semiconductor by putting in these carriers, and can you like write device? Make a device.
Oh, yes. Oh, yes, you sure can. We've done that with strontium titanate. We used a blue laser to write a low resistivity path on that crystal. So you could definitely use that to define highly conductive regions on a semiconductor.
Can you have other impurities in there, so you're actually activating it in some way as a doped semiconductor?
Let's see. I think. Do you mean like introducing more or less of a particular impurity, or?
Yeah, I mean, populating the electrons. And this may be a silly question.
Well, I'll answer Okay, so there is a lot of interest in using light to to change to kind of influence the diffusion of impurities. And so if you could get impurities to diffuse faster or slower based on shining light, you could move them around and design an interesting device that way.
Right.
Yeah, what about UV? So
Yeah.
so if light comes through in the red, it's transparent, and the problem if it's green, it gets absorbed. Just wondered, so that excites an electron.
Right.
What are the pathways for the de-excitation?
Oh, sure. Yeah. Well, one is to emit red light. Sorry about this. I mean, we'll do it any faster. I passed it up, didn't I? That's what happens. Oh, there we go. Okay. So, yeah, so you have this green absorption for ruby. You also have it in violet, which is harder to see with your eye. But once you excite to that level, it decays by non-radiatively, so just heating up the crystal. It decays down to this level called E2. And it can live there for a while, milliseconds. It's a, and that's what helps it be a laser. Anyway, the transition from E2 to A2, the ground state, that is what produces the red light. There are non-radiative ways. So non-radiative emission pathways would include producing lots of phonons. You could, if there are defects in the crystal, you have something called Shockley-Reed-Hall recombination. So if there's a defect in the middle, the electron might go to the defect and then down to the ground state. But this is highly efficient. So Ruby is very, very, very good. Most of the decay is radiative.
So,
back to photochromism and your hydrogen obsession. My question, why were you showing hydrogen always with like 2 electrons? Are you
Yeah, well, hydrogen. Well, it's interesting because it's, I hate to say this, but like in the semiconductor world, they call that H plus. Because it's plus compared to the oxygen 2 minus that it replaces, and others call it H minus. So a bit of confusion can result. But yes, so the oxygen vacancy. So imagine you have an oxygen 2 minus. Okay, oxygen covets 2 electrons. That's the only chemistry I know. So you have oxygen 2 minus, and you take out the oxygen atom, but the 2 electrons remain. Okay, so that's an oxygen vacancy. And then you put a proton in there, and that's what I'm talking about.
So related question to the guys. It's what the persistence of the materials where you create these free carriers really seems remarkable to me, like weeks, hours. And I'm amazed that there aren't other pathways by which that resistance is kind of restored.
Yes.
And I guess, I'm speculating that what it comes down to is the strength of that OH bond.
It's exactly it. And so if you have a pure crystal, bulk crystal, interface effects and devices can lead to persistent photoconductivity, but that's icky. Amorphous things are icky. So let's just say there's a crystal. There is no way you could have 2 weak persistent photoconductivity with just electrons. They will find their way back. Okay, they're electrons. They're fast. Just forget about it. So exactly what you said. The strength of the OH bond is what gives it that persistence. So that has to be broken before everybody can come back home.
Just a historic comment about optics of defects in crystals in the WSU physics department. It's a much longer history than you may realize. Between 1980 and 1990, Professor Brownwick was here and studied various defect mechanisms having to do with absorption, but more importantly, developed thermoluminescent dosimetry.
Oh, yeah.
Came up in this discussion, using CO2 lasers to do the glow curves.
Oh, interesting.
And then that led to perhaps the first physics-related company in the WSU Research Park. It was called International Center Technology. It was there from around 1989, I don't remember, until about 1998.
Yeah.
Anyway, so there's.
Wow.
And Brownick essentially left physics department and then just to run that company. And then the company was bought out and moved. But any event, there is a long history
Wow.
of defect optics and crystals experimentally in this department, much more.
Yeah.
Than I think anybody here might remember who I thought I would.
Oh, that's excellent. I had no idea. Thank you.
I guess two questions. You talked about the two kinds of defects, like the shallow defects for Photochromism sites.
Yeah.
And then the localized where one goes to maybe nearest neighbors.
Yeah.
So what would define the barrier between those two? If you had one that had next nearest neighbors, that's
Mhm.
will be shallow.
Mhm.
And following up on that, if you could, engineer some sort of defect that kind of was exactly on such a barrier,
Mhm.
what that would do to the crystal.
Yeah, well, that's a neat question. So I think it's really tough to have a meso, defect that's sort of deep, but sort of not. Because what happens is that imagine so hydrogenic, you've got the Bohr radius, right? So let the Bohr radius get smaller and smaller. The thing is, there's a perturbation at the impurity site. So it's not perfectly hydrogen. It's actually right at the impurity, it's a much deeper potential energy for even for a shallow.
Okay.
But that perturbation doesn't matter too much because the wave function is huge. But now as you let the wave function get smaller and smaller, it's going to see that perturbation more and more. And then suddenly you get it just almost like a sudden transition, it becomes deep. So there's not a whole lot of halfway
I see.
defects.
So it's binary.
It's sort of binary, yeah. Yeah, this is very interesting.
Check your chat.
Yeah, I think there may be comments or questions, and then we can
Now I
finish
know
up with those.
Just wiggle your mouse.
Wiggling and pushing escape.
Your mouse by the
Oh,
green.
here we are. Chat, okay, thank you. Chat. Two minutes. What level of light exposure? So the light exposure needed to induce persistent photoconductivity can be very, very low. You just have to wait longer. So we haven't looked at, how many photons, but it can be a very low intensity over a longer period of time. And can be used in inks and tattoos rather than some other metals, thermoluminescence. Oh, thermoluminescent tattoos is an interesting application I hadn't thought of, but I like applications, so that's pretty interesting. That would be fun. Actually, people are into fabrics that show color, and so it's a big field. So yes.
All right. Maybe we finish here. Thank you very much
Okay.
for the talk.
Thank you all.
Thank you.